Good morning, everybody, and welcome to the Treasures midterm webinar. So we are very happy to have you online today and hear all about the great work that we've already done and the results we've gained so far at the midpoint of our project. So we're looking at these local circular economy solutions to solve global challenges that we're all battling with. Before we start, there are a few house rules. So make sure that your speakers are on, your microphone is muted. You can raise your hand and use the chat to ask questions. If you want throughout the presentations, you can already write into the chat if there are any questions that pop to your mind. Comments are also very, very welcome. We will then take these during the Q&A. So shoot us with your best questions and let's engage in a very rich dialogue today. And also please note that the webinar is recorded and we're sharing the recording afterwards. So in case you don't want your face to be seen, then keep your videos off. Could I have the next slide, please? So we have structured the webinar today into 3 different sessions, and the first one is focusing on the circular plastics work that we do in our Treasures project. So we have a few different presentations throughout the day for the next few hours that is then finalized with a Q&A. We are comparing a little bit mechanical and chemical recycling as complementary technologies. We are revealing a little bit what we've done with the stakeholder engagement. So there's a wide range of variety of activities that we've done regarding stakeholder engagement to enhance the circularity of plastics. We've done very extensive operational environment reviews, including legislative reviews that have now turned into policy recommendations. We have created a sustainability assessment system dynamics model that will be introduced. And then the cherry on top of the cake is the replication handbook that we've done in our project that will be presented as well. So if you take the next slide, you can see the speakers for today. They will introduce them shortly in the beginning of each presentation, but we have presenters from different partners in the project, research organizations, counties, cities, and so on. If we take the next slide, I will try to recap our very complex project in a few sentences, few minutes. So the treasures, the name actually comes from the idea that the treasure is in the resources. So we aim to initiate systemic change by developing technologies and systemic circular economy solutions. And we're targeting 3 different value chains. So we have the plastic waste, end-of-life electric vehicle batteries, and bio-based side and waste streams. And how we define systemic circular economy solutions, we see that there are kind of 2 angles to it. So we have the key value chain demonstrations where we do more technical type of development. And they are coupled with very thorough list of stakeholder engagement demonstrations. And these stakeholder engagement demonstrations is something that is crucial to really be able to implement and adapt these circular solutions into our everyday lives. So we are mostly focused in the Nordic region. Oh, maybe if you go back just a second. Yes, thank you. So we're mostly focusing, demonstrating these in the Nordic region and then replicating these solutions in the Baltic Sea region. The idea is in the project that we develop, we implement, and we replicate. So we get learnings also on how can we multiply the solutions that have been developed to and openly share them to gain maximum value for the European citizens, cities, and regions. So the solutions that you hear today, please make a note. This could be something that you can implement. It doesn't really matter where you are. We are hoping that we can inspire different stakeholders and maybe also create a little bit of interest into the solutions that we're developing, and also accelerate the possibility of taking up the solutions we've developed for further replication. But then let's actually go into the detailed presentations by Stefan and Ugur for the mechanical and chemical recycling as complementary technologies. So we're happy to present the results so far from this work. Please go ahead, Stefan and Ugur.
Okay, thank you very much, Anna. So this is Ugur Kaya, working as a senior scientist in VTT for about 3 years. And maybe Stefan, you can also introduce yourself and then we can get to the presentation. You are mute, Stefan.
Of course. My name is Stefan Kubowitz. I'm working in SINTEF as a senior scientist in the group there for polymer and composite materials. Yeah.
Thank you, Stefan. Next slide, please. So we would like to introduce you a bit about the complementarity of mechanical and chemical recycling. But before that, let's go through some of the facts in circular plastic. Here in this slide, we see there are many ways to solve the plastic circularity problem currently. And especially for the circularity scenario, we see 8 different methods, like intervention levels. And first, the first one is to eliminate unnecessary packaging directly at the source or through the product redesign to reduce the packaging waste. The second one is to reduce the plastic packaging by reuse and new delivery 2050. And also reduction can be done by the stock and corresponding automotive plastics demand by 22%. And this also applies with the sharing economy and new service models. The fourth one is to substitute plastic packaging with the paper and compostable alternatives. And this is also aimed very much towards 2050. Design for recycling is one of the most important aspects to tackle with the plastic circularity, and this decreases economically unrecyclable packaging by 30% and increases the vehicle dismantling rate up to 15% for high quality recovery of the automotive plastics. And one of the other very important aspect is the expanding collection for recycling. Apart from sorting, it's also important to enable the collection at the source, and also this will also be combined with the easy to recycle, easy to dismantle approaches, so that you will get better, higher quality secondary raw materials. And mechanical recycling is one of the most important recycling techniques, but it's also the most established recycling technology actually. So it's really essential to increase the mechanical recycling capacity. On top of that, chemical recycling capacity also has to be increased. So next slide, please. Here in the slide, we see on the horizontal axis, we see different polymers. And on the vertical axis, we see different applications of these polymers. And this matrix shows you how complex and how heterogeneous of the whole plastics industry. They exist in almost all aspects of our lives, but the majority is actually the packaging, building and construction, and let's say also the others. But when we look at how much mechanical and chemical recycling is used for post-consumer, is construction is more dominant there, and we see high potential for packaging plastics actually. And for the post-consumer, pre-consumer and post-industrial waste, mechanical recycling is more dominant. Overall in Europe in 2022, only 18.6% of the plastic waste is mechanically recycled, and very minor of the is chemically recycled. Next slide, please. Here we see 2 different strategies for collection of the plastic on the left side, we see mixed waste collection, which is almost the half of the entire collection. And on the right side, we see separate waste collection. The difference between these 2 collection strategies is that you are able to enable recycling substantially more higher in the separate waste collection. And then eventually you decrease energy recovery rates, which is in competition with the recycling currently. And also you substantially decrease the landfilling, which pollutes the environment, of course. And in total, when we combine these two different waste collection strategies, you are able to reach only 27% of plastic. But how to enable the increase? We first have to increase this collection and more plastic waste to chemical recycling to enable. One of the technologies is the advanced and optimized sorting and washing, so that we are able to reach both higher secondary raw material quality and also recycled plastics quality for new applications. Next slide, please. And if we can also click 3 times more, we see the slide entirely. Thank you. So on the right side, there is a route, and this journey is for mechanical recycling. This is a typical process for mechanical recycling of plastic packaging waste. And before that, you have to go through all of these 8 stages. It has to be first collected well, and then it is just fed to the shredder through the conveyor belt, and it goes through metal separation, and then wind shifter and sorting techniques, grinders, washing, density separation, and drying. So all of these pre-treatment stages are essential depending on the waste feedstock types. What are your typical products? Are usually polyethylenes and PET and polypropylene and some mixed plastics. So they are usually polyolefins. And at the end of the day, you also have a rejected portion, which is almost 50% of the fed plastics. The question is, are they suitable for energy recovery or suitable for chemical recycling? Because they are not suitable for mechanical recycling. Next slide, please. Of course, mechanical recycling is the most established method and conventional method in the recycling industry, but chemical recycling really complements mechanical recycling by providing new possibilities, because it is basically able to recycle polymers for food contact and other demanding applications. This is one of the legislative topics where you have to clarify and prove that your recycled material is able to be food contact, which is a little bit difficult with mechanical recycling technology. And chemical recycling is also able to tackle fractions where you cannot deal with mechanical recycling. For example, if you have a mixed polyolefins or multi-layer packaging and polypropylene films, chemical recycling is able to recycle it up to a certain percent. But chemical recycling requires further technology development for higher technology readiness levels, and this has to be enabled because we need to enable recycling of lower quality plastic waste than today. And also a new legislation is needed to approve as recycling method of chemical recycling to enable use of certified mass balance approach. Next slide, please. And one more click. Yes, one more. Yes, so the new future concept is actually parallel mechanical and chemical recycling utilization enabled by optimized sorting in the core. So after plastic waste sorting, you have 3 routes: one, energy recovery; 2, secondary to mechanical recycling; and the third one is chemical recycling. Mechanical recycling needs better sorting and washing, and it needs tailored. It needs to be the fractions has to be tailored with additives and blending with virgin plastics, and design of optimal applications for recyclates is needed. But also it enables the removal of feedstock variation by adaptive process control tool, for example. This is one of the new upcoming technologies which we are also using. In chemical recycling, it's an alternative for incineration or recycled petrochemical feedstock, and it is used when petrochemical feedstock is needed from the recycled feedstocks. So it's but there are also some needs, as we have discussed before. You need more improved plastic to plastic recycling yields. You need to lower the carbon footprint. and also use of highly mixed plastic waste and optimized sorting is the main objective of chemical recycling. Next slide, please. In this slide, we see one of the mechanical recycling technologies that we use. This is Modix extruder for plastic waste pretreatment. So this mechanical recycling technique is a pretreatment to chemical recycling, let's say, or it can be also a pretreatment for mechanical recycling. So if you look at the traditional process of mechanical recycling or compounding, if you have a bulky waste or like a side stream, you can imagine as like a big plastic part, but then before going to extrusion, normal compounding process, these bulky plastics has to be shredded, milled, or grinded. So then you will be able to just feed those pellets to the extruder, and then you have a homogeneous material, which is the objective, one of the objectives of compounding or mechanical recycling. In the alternative process that we have developed in VTT, it's a modular extruder, which is also giving the name to Modix. You are able to feed bulky plastics in different forms. It can be a textile, it can be a whole plastic part, or granulates or films right away to the extruder with a big feeding zone, and it gives you a homogeneous and compacted material at the end. So this is very essential for chemical recycling because it needs homogeneous feed. But this is a little bit different material. Next slide, please. This is another mechanical recycling technique that we use in our premises in VTT. This is called Varex extruder, but this is to really upgrade the feedstock. So this is a new mechanical recycling tandem extrusion line with adaptive inline melt rheology control. This is able to stabilize and upgrade the properties of recycled plastics by applying different tools and techniques such as melting and filtering of recycled material where you cannot really tolerate the foreign particles. It enables smart dosing of additives like virgin polymers, stabilizers, compatibilizers, chain extenders. So it's able to fine-tune the compound formulation on the fly. And also you can upgrade the properties and homogenize the feedstock by, for example, with several physical parameters like viscosity, thermal, mechanical properties, and then at the end of the day you reach ideally virgin-like polymer properties. This is really ideal for R&D and new material formulations, but also can be easily adaptable to industrial lines. We are also able to monitor the degradation of plastic process in the melt phase, which is really important because in all mechanical recycling stages, you are facing some degradation. And the target groups of this equipment is basically all recyclers, converters, such as film producers or injection molders, or OEMs, let's say, original equipment manufacturers. Next slide, please. This is the chemical recycling technology that we apply in Treasures project. This is called pyrolysis. And you imagine if you have your plastic waste, it has to go through all of the pre-treatment stages. It can be like this previously described mechanical recycling, but it also can be grinding, shredding, washing, drying, or some sorting, because you also need to sort out the materials that chemical recycling also cannot tolerate. And then you go through pyrolysis reaction. We use BFB technology, and then the pyrolysis oil is upgraded to be fed to the commercial environment, to the industrial equipments of petrochemical industry. Let's say to produce new monomers or new polymers. And at the end of the day, you produce a liquid oil, just like the one picture in the right-hand side, and also wax. Next slide, please. So, of course, the pyrolysis products also depend on the various plastic waste that you have. For example, if you have polypropylene and polyethylene, the pyrolysis product would be most likely waxes, paraffins, oils, and gases. And then if you have polystyrene, polyamides, or polymethyl methacrylate, then you get a styrene and its oligomers from polystyrene, or caprolactam from polyamide, or methyl methacrylate from MMA, PMMA. And if you have polymers like PETs, polyurethane, PVC, then you get acidic degradation products and gases, char, and chlorine impurities. After going through the pyrolysis, during post-processing, you apply stages like fractionation, hydrogenation, steam cracking to olefins. Of course, then you also need to separate and purify the contaminants depending on your pyrolysis product and the feedstock. The end products can really vary. You are able to obtain almost like virgin-like polymer, almost virgin-like feedstocks, building blocks, such as oil refinery feeds, chemical products, monomers for polymers, and chemicals and fuels after upgrading. Next slide, please. In the slides, we have a brief view for the factors affecting the product distribution and pyrolysis. When we divide the pyrolysis into two different technologies, one is the thermal pyrolysis and the other one is catalytic. For the ones who are a little bit familiar to these technologies, catalytic pyrolysis is more able to focus and can further narrow down the product spectrum. But in thermal pyrolysis, the products are rather a mixture of liquid and wax, so mainly waxes basically. And you have a wide boiling point range for the products and carbon number, really varying between 300 to 550 degrees Celsius, and carbon numbers from 10 to 40. And but also higher temperature and residence times can shift the product spectrum towards the lighter products. This is also one feature of thermal pyrolysis. In catalytic pyrolysis, this is more selective. This enables more selective conversion of plastics into lighter hydrocarbons or aromatics instead of heavy waxes. So this is really advantages, and you're able to tailor your products towards your needs. And olefin-rich gases can be produced with acidic catalysts, for example. This is also one tool that you can utilize. And you can also see them on the previous slide. But thank you. I can give my words to Stefan for explaining Traeger's concept a bit more.
Yeah, thank you, Ugur. So in the Traeger's project, we looking at like plastic waste from 3 different areas, or like industries and ways: agricultural plastic waste, municipal, which is basically household waste, and then industrial plastic waste. And during the project, we then look also then a bit on collection and how that could be optimized for the different streams, then pre-treatment and sorting options. And then from there, we go to the mechanical recycling that Ugur was just explaining, and also chemical recycling. So the aim is to identify which streams are suitable for which route of recycling. And then from the mechanical recycling, we will get mostly recycled plastics. And from the chemical recycling, as seen just before, we have all different kinds of chemical products that can be then used in the chemistry or chemical industry. Next. There. So, and we looked at different waste streams. So just to come back a bit to what we already heard about the leftover from the sorting. So there is already mechanical recycling of plastic packaging waste. So the most, or the easiest fractions, they get already removed by automatic sorting or manual sorting. And then we are left with still quite a portion of plastic that can actually be used or at least we are trying to look into how we could use what is left after the first round of sorting. And there we see that there's still more than half of it is still polyolefins, so polyethylene and polypropylene. And that's actually a very good feedstock for the chemical recycling. Because of this variety of materials, it's not that a good fit for the mechanical recycling. But for the chemical one, it's definitely suitable. And what we see here, it's also a relative large portion of PET, which would need to be also removed or separated from that waste, and can go to separate PET recycling. There may be also chemical recycling of PET. Yeah. So in the project, we were looking at 10 different feedstocks from different industries or places. So we had the municipal waste from both Norway and Finland, and we had some agricultural wastes, mostly from Finland, and then some industrial waste from Norway and Turkey. And there we kind of analyzed already a bit the composition of the material and did some tests. And we can say that the municipal waste is completely, or most of the waste is suitable for chemical recycling. And some fractions are also for mechanical recycling, or can be used for mechanical recycling. So the quality is still good enough to get some reasonable material out. Yes. So some examples from the feedstocks that we looked at. So one is, for example, municipal rigid plastic. Here, that we are talking about plastic chairs, pipes, containers, buckets, all these kind of larger plastic items, which are not necessarily packaging waste, and which also is not recycled in the same way, because all the recycling that is done is mostly focusing on packaging waste. So here, Eco-Company, together with the Tampere University of Applied Science, made a small sorting campaign where they looked through almost 2 tons of plastic wastes that were collected in some recycling place in Finland, and analyzed the composition, and also there saw that about 85% of the plastic is polyolefins, which means polyethylene, polypropylene, and some polystyrene also, and a small portion of PET, PVC, and other plastics. So again, there's a large potential for both mechanical and chemical recycling in this waste stream. Yeah, next. Second feedstock I would like to show you is agricultural plastic waste. These are, for example, hay bags, which you can see the white things lying around on the fields, but also other types of packaging films and plastic used on farms. And here we did some collection on an individual farm, collected about 20 kilograms of plastic, and then sorted the material and looked at the composition and the properties. And in that case, it was all 100%, it was all polyethylene in various types and shapes. And this material is definitely suitable both for mechanical and chemical recycling. And so there is again a large potential there for reusing the material. Also there, thanks to Mikko, who was a master student in the project. And lastly, we have also here an example from municipal waste from Fredrikstad in Norway. There it was just unsorted plastic waste from the municipal, and we sorted it then ourselves, either by just looking at the signs that are on the packagings or by using spectroscopy. And we saw again the composition is very much polyethylenes and polypropylenes, and then a smaller portion of PET. So here we removed what is again easy to recycle, the 4 ones on the right side, and on the upper right side you see some examples of packaging which is definitely not suitable for mechanical recycling. These are multi-layer packagings. These are packagings that have metal coatings or excessive amounts of ink on it. And so this needs to be anyway sorted out before mechanical recycling. But some of it might be useful for chemical recycling. So that's something that we want to look into. Next. So as a summary, the challenges and gaps that we found so far in our work in the project is that we have also divided these in different stages of the process. It's already during collection and pre-treatment it starts. So the waste management can be quite diverse. So you have different systems in different regions. Even within the country, it might be different. So the collection can be tricky. You can have large distances, especially, for example, when you collect agricultural waste, there might be large distances between the farms. So that needs to be organized and also dealt with. And then you have the supply and trade of the feedstock. So there are export rules. If you want to cross borders with plastic waste, that might be or is a challenge. Then about ownership of the waste. So there's lots of policy and regulations behind that need to be aware of, but also there might be some things that would need to be updated actually to improve the situation and kind of help to have higher recycling rates. Then on the recycling types, you have different, the 2 different recycling methods that can be improved. You have the design for recycling, where it actually starts, how you design your product or your packaging, that already kind of defines how easy it is to recycle. And then on the production side, there's also still a lack of capacity and investments to kind of go ahead with this in full scale. Next. So at the last thing to summarize a bit and say, okay, what were the key takeaways from the first part? So efficient recycling starts already with the collection and the pre-treatment and sorting. So the better the materials are sorted, the better you can recycle them and the higher the quality of what you get out. Different waste streams may have different hurdles. They may have different ways of collection, different pre-treatments. So everything would need to be kind of like streamlined for each waste stream. There's a lot of potential in agriculture and municipal plastic waste. That's what we saw already during our tests, and these materials are actually quite well suited for both mechanical and chemical recycling. And the mechanical recycling can work well together with the chemical recycling as a pre-treatment or step before. And also they can be worked in parallel. So one part of it can go in one direction and the other in the other. And so the focus is here on like, okay, reducing the amount of plastic waste that needs to go to landfill, and then kind of using the full potential of both recycling methods. Okay. Thank you.
Very good. Perfectly on time. Thank you very much, Stefan and Ugur. There's actually one question in the chat that maybe we have time to take quickly. So are there any big plastic recycling plants in Europe, and what is the European plastic currently? Where is the European plastic currently recycled?
I know that there quite some recycling, plastic recycling is done in Germany, and I think also in Sweden. There might be also some in other countries, in Lithuania maybe. So it depends a bit on the waste stream, but I think a lot of the packaging waste is also going to Germany for recycling currently, at least from Norway. I mean, Norway is there's just some local recycling of some plastics from aquaculture, that's done in Norway. But the bigger volumes, like packaging waste, is mostly going abroad.
Yeah, maybe I can also support a little bit. So if we think about the mechanical recycling capacity, we're about, I think, at 12 million tons at the moment for last year. And if we use about closer to 60 million tons, so there's definitely a gap. And then even from the capacity to what actually gets recycled, there's quite a lot of export still. I think Turkey has become a little bit of the new EU solution for plastics recycling. So there are also quite a lot of exports. But I actually posted in the chat from the European Environment Agency, the circularity metrics app, where quite good data can be found on the circular status of plastics.